Is it okay otherwise? It's like, any questions? All right. All right, so as for today, we're gonna finish up the rest of chapter 6, part 2. And then we have spring break, some time off. And we're gonna lecture 7 upon that Tuesday on return, and then we have our quiz on this. All right, so like I said, all right, like I've been telling you guys, survive chapter 6. All right, and this should be a little better because at least we're back to solving some problems. I want to point out one big thing. So when we have an equation that looks like this, x times x plus 1 equals 0. We break this into 2 individual equations. And we've been doing this so long, I just want to refresh. This is the zero product property. And you may not have heard it called that. And the reason this works, right, is because when I divide one equation, right, anything, 0 divided by anything is 0. And this is why this works. We can break anything that you can get into factored form and everything being multiplied into individual equations. Only if the other side is equal to 0. And I bring that up because the problem we're about to look at, sine theta times cosine theta equals -1/2. I see people wanting to do it when it is a value other than 0. So we cannot solve that equation using, oh, well, how about the 1/2 product property? No, it doesn't work like that. Right? It only works with 0 because 0 is special. 0 divided by anything is still 0. And that's why, right, we can actually do this property. Which means, back to our example, in order to solve this, we have to think of another way. Now, good news for us is that sine theta times cosine theta is close to something we've been working with. Specifically, sine 2 theta equals 2 sine theta cosine theta. That is something we can then deal with. Because that's pretty close to what we're looking at here. If I divide both sides by 2, this is a double angle identity. If I divide both sides by 2, then I have exactly what I have here. And I've reduced, right? So we talked about reducing multiple trigonometric functions down to 1. And this is always, if we can, something we want to do. Now, the other thing is we talked about, oh, well, we really love it when it's just thetas. So this took it from thetas to 2 thetas, which means we have to do that 2 pi k adjustment. But I reduced it from 2 trigonometric functions to 1. So our equation now becomes 1/2 sine 2 theta equals -1/2. Then multiply both sides by 2. And actually, this simplifies down relatively nicely. And we saw last time with all these trigonometric functions, graph the standard sine, cosine, or tangent function. And identify its solutions, assuming theta was not adjusted. So in this case, all right, again, our standard sine graph, right? The more of these you do, the more that those three functions just get etched into your memory over and over and over again. Thanks. So, all right, where is the standard sine graph equal to -1? Or what angle? Do we remember what we were doing? Or are we all ready for spring break? -1 is down here.
3 pi over 2.
Almost.
3 pi over 2.
3 pi over 2. All right, that guy right there is 3 pi over 2. Pi over 2 is right here. So that means I have the solution 3 pi over 2. And our angle 2 theta equals that value. And then this is where I need to do plus 2 pi k. And this is also a situation where you only have one. Remember, a lot of these we actually have two solutions, right? But we happen to be all the way at -1, which means there's only one solution between 0 and 2 pi. And so that 2 pi k that we add on, which is the shortcut to basically regraphing the whole function, divide this whole thing by 2. Theta equals 3 pi over 4 plus pi k. And then remember, in order to find our solutions, you basically start picking k's, integers, non-negative whole numbers. 0 is the easiest one, which gives me 3 pi over 4. And then just keep going until you hit 2 pi, or whatever the range is in this case, 2 pi. So 3 pi over 4 plus pi times 1, which is 3 pi over 4 plus 4 pi over 4, common denominator, 7 pi over 4. And I already know that that one's the highest we can get because 8 pi over 4 is 2 pi. And so you can always keep testing. You can keep testing the values. Go to the negatives, go to the positives, make sure you get them all, right? But as soon as you realize that that's your limit, we could just stop. Which then, so theta equals the solution set, 3 pi over 4 to 7 pi over 4. Or and, not 2. Easy peasy, huh? All right, now we're gonna do one that's really fun. Sine theta plus cosine theta equals 1. Multiple ways I could approach this. One is I could use, right, if I have sines plus cosines, does anything spring to mind? If nothing springs to mind, that's okay. Because if we go to x plus y equals 1, all right? So just standard substitution that we've done. This is kind of an equation that's like, gosh, I don't even know how to solve this. But there is a relationship, all right? Something that we should be familiar with. If you square both sides, it's a common technique. in algebra. We square both sides of our equation. That gives me x squared plus 2xy plus y squared equals 1 still. This then creates something we can solve. And this is actually an equation that you are familiar with, even though you might not initially recognize it because the form is kind of weird. This is the equation of a circle. The equation of a circle also relates back to trigonometry because x squared and y squared, and notice I didn't identify exactly which one was x and which is y, but it doesn't matter because x squared plus y squared is going to equal a wonderful number for us. All right, once we put these back into the trigonometric functions. Once I have this back in this form, does anything look familiar? Yeah, I have the fundamental identity there. And even better than that, after we do that, watch what else happens. Subtract 1 from both sides. And now that I have this, all right, what was that property we were just talking about? That algebraic property? Zero product. The zero product property. Now, I actually have two approaches here. I can use the zero product property, or what is 2 sine theta cosine theta?
A double angle.
That's the double angle, all right? That's the double angle for sine. So actually I have two approaches. Since we just did the double angle, let's actually use the zero product property just to make sure we're familiar with that. Because there's situations where maybe this didn't work out. If this was sine theta and that was sine 3 theta, I didn't have an option. So I want to make sure that we can do this both ways. So if I'm going to use the zero product property, I can do one more step. I'm going to divide both sides by 2 to get that out of the way because that's not helping me. Sine theta cosine theta equals 0. Then the zero product property says, well, that means sine theta equals 0 and cosine theta equals 0. Now I have two trigonometric functions here, but they are both in their most base form without theta being adjusted. So I have two individual equations to solve. That means, let's do sine first. The range on this was 0 to pi. Okay, just making sure. All right, so this one we're solving sine theta equals to 0. So for what angles is the function equal to 0? Zero and pi. Now, would it also be 2 pi? No, why not, Charlene?
Because it's not included.
And that one's tricky. So we gotta make sure we're checking our limits on this. Technically, does sine theta hit 2 pi? Absolutely. And every multiple of pi forever, okay? This is why we gotta make sure what range are we in. If this was equal to, then I would have put 2 pi in there. But this specifically said 0 including and 2 pi excluding. So our angles here are then 0 and pi. Okay. This one then, we also are lucky enough, we get to look at the cosine graph. And we're doing the same thing here. Cosine theta equals 0. And basically we identify for what angles is the cosine function equal to 0.
1/2 and 3/2.
Absolutely, right there. There's 3/2 and pi/2. So the zero product property can be very, very helpful, and especially the more complicated the functions we have. This is always the way, but it has to be to 0. And that's our key point there. All right, so putting that all together. Theta equals 0, pi/2, 3 pi, and then 3 pi/2. So all those solutions. Now, here's the big problem with our approach here. When you square, all right, in general, when you square an answer, how many solutions, and actually it's more like the other way. When you square root an answer, how many solutions do you get? 2, right? Square root of 4 is plus or minus 2. Well, the same problem happens in reverse, right? When you square an answer, if you only had 2 solutions, how many solutions did you end up with? 4. It doubles, right? It's to the power of 2, right? If you were supposed to have 3 solutions, it would be 3 squared. You end up with 9 solutions, which means that we actually annoyingly, because we squared in order to get here. We need to check our solutions. Extraneous answers. And again, this is another, now, ideally, should you always check your answers? Yeah, okay. Have we not really checked them so far? No, because we haven't done anything that actually gets us a multiple and an abundance of solutions that might not be correct, right? Everything we've done until this point, as long as we followed our steps and didn't make a mistake, right? There was no reason to like verify, even though you always should, right? This is a case where we did something that is correct in algebra, but it becomes problematic because it adds extra answers. Now, the good news is that in order to check this, use our starting equation, which was sine theta plus cosine theta equals 1. And, all right, we have good news. At least all these were pretty easy. So check theta equals 0. Sine of 0 plus cosine of 0. All right, sine of 0 is 0. Cosine of 0 is 1. Okay, good. 1. So that one's okay. Okay, sine of pi/2 is 1. Cosine of pi/2 is 0. Oh, good. That one makes 1. Sine of pi is 0. Cosine of pi is oh no. So that one didn't work. And same thing, sine of 3 pi over 2 is -1 plus cosine of 3 pi over 2, which is 0, which is -1, which means that one didn't work either. So actually, theta equals 0 and pi over 2. And that's the tricky part. As far as that solved, I was like, it was pretty straightforward. All right. Squaring is a very, very common technique, right? But notice that we squared here. Usually, when do we decide to square a function or a set of functions or an equation? What usually indicates, gosh, I just square both sides. When you have what first?
Can you repeat the question?
What? When do we square functions? When do you square an equation? What indicates, gosh, I should square both sides of this?
There's a square root.
Yeah, there's a square root, right? We're in, like, the basic concept of algebra is do the opposite. If I see a square root, the first thing that pops in my head is square. I was like, I squared this because when I looked at this, I was like, x plus y equals 1. I don't know what to do. So I just think of what's the common stuff we do. Oh, I could add this over, but it's not going to change anything. But because I have sines and cosines, I'm like, oh, you know what I do know? I know the fundamental identity. So if I square both sides, I think that's going to lead me somewhere. All right. And so this initial step, although not complicated, is not the first thing we think of. All right. Okay, so we've done a lot of sines and cosines. Well, don't forget, there's tan, right? And there are reciprocals out there. Now, whenever you have secants, cosecants, and cotangents, you convert them always, right? When solving problems back to their reciprocal functions. But tangent is one where we can solve directly. But we need to remember a little bit about the tangent function. So our basic tangent graph, the biggest part about tangent that separates it from sine and cosine is the period. What is the period of tangent? Pi, right? It is not 2 pi. So those questions where we add 2 pi k, that's when the period is 2 pi. So for tangent, when I have an adjusted angle, I'm not going to start with 2 pi k, I start with pi k. And that's the big trick that usually gets everybody. Otherwise, all right, we still do the same things. All right, now the graph is not nearly as clear, but I still look, okay, root 3 is about here. It only hits tangent at one point. And then we say, for what angle is tangent equal to root 3?
Wait, how'd you know root three's there?
Oh, it's about right here. Root 3 is somewhere between root 1 and root 4, so it's somewhere between 1 and 2. It's about. I was like, it is a positive number between 1 and 2. There's no scale on this, right? Like, I was like, Root 3, I think it's like 1.7 something. That sound right?
Yeah.
Yeah, okay. I was like, and so I'm like, I know it's up there. It's not down here. I know it's positive and it's about that. So it's hitting one number. So, all right, for what angle is the standard tangent graph equal to root 3?
Pi over 3. Pi over 3.
Pi over 3. So we start with our pi over 3, and now plus pi k. All right, because the period of tangent is pi. And that's the adjustment. Otherwise, everything else is the same. But oftentimes, right, if we start with 2 pi k here, everything's going to get messed up. So just remember the period of tangent, pi. So we're coming back, right? We're using a lot of the stuff we've seen already in order to solve these problems. All right, so let's see. This gets us theta equals 2 pi over 3 plus 2 pi k. And actually, k equals 0, which is 2 pi over 3. And as soon as I do k equals 1, I'm past 2 pi. My restriction is 0 to 2 pi. So that is the only answer. Which means, well, that wasn't. It's possible that there could be more solutions depending upon the range. But in this case, my big goal is just to make sure that we start with plus pi k. All right. And then continuing to remember the tangent graph. Actually, it does remind me of one more thing. Tangent actually has a funny thing too, that our first value, if this was negative, our first value, so k equals 0 wouldn't work, right? So let's pretend it was negative root 3, which means our first value, could be negative pi over 3. So k equals 0 wouldn't work, and I'd have to go to k equals 1. All right. But the point is to keep guessing values of k until you get in that range and fill all values that are possible. Okay. All right. So this, all right, should look very similar to that problem we just did, whatever it was, example 9. Cosine of an angle plus cosine of an angle equals 0. And we could approach this the same way. All right. What's a good technique? There's not much I can do here algebraically to solve this, so I could square both sides. And I could do the same approach that we just saw. And this is what I was asking you before. I said, oh, if I have sines plus cosines or cosines plus cosines, I was like, does anything spring to mind? This one should be a little more obvious of something that springs to mind. Does anything spring to mind on this one? And cosines plus cosines and sines plus sines and sines plus cosines. Sum to product. Now, be aware, on this example 9 that we did, could I have used sum to product on this one? Yeah. It's just theta is 1 theta and 1 theta. So I could absolutely use it on that one too. I'm glad no one said it because I wanted to do it this way to show you, all right, other techniques. But there's always multiple approaches, all right? Whatever springs to your mind first, do that. I was like, there's always going to be multiple ways to solve things, right? This is math. The point is lots of approaches. And if you really want to do a good job, solve it multiple ways in order to make sure all the solutions match up, just for practice, just for fun. All right, this one definitely for me, sum to product springs to mind. And it springs to mind too, because as soon as I get past like 2 thetas, and actually this is still evens, so technically double angle and double angle, all right? But as soon as I get past 2 theta, I want to reduce this down, and this is equal to 0. So I mean, sum to product, 0 product property, it's all right there. And so again, those sum to product properties, I use the formula just like you guys do. I look for the one that has cosine plus a cosine, and then I write it down. I mean, I don't have those memorized. They're too annoying. All right, so let's see. We got 3 theta. Sine of 2 theta over 2 theta. To make my life simpler, I'm going to divide both sides by 2. Whenever you can get rid of a coefficient, get rid of it. And then once again, all right, this is also why sum to product immediately came to my mind, because I have cosine of a function times cosine of a function equals 0. So I know I can once again use the zero product property. And we've already done this one too. So actually, the good news is both of these, even though the angle is adjusted on this one, both of these are cosine of the base function equals 0. And we already identified this. It is at pi over 2 and 3 pi over 2. Now, good news, this one on the right is done. Cosine theta equals 0. Well, theta is pi over 2 and 3 pi over 2. So this one, I already have my thetas. This one on the left here, cosine 3 theta equals 0. Since the theta is adjusted, I need to do the 2 pi k adjustment. So 3 theta equals pi over 2 plus 2 pi k, and 3 theta equals 3 pi over 2 plus 2 pi k. So we need to adjust it. And remember, both solutions, right? Both are, I mean, it's almost never more than 2. If there was 5 solutions, then you would do all 5 and adjust them and find every value of k for both the possible equations. All right. Divide them by 3 to get theta equals . And then before I start doing the K's, and this happens a lot, I just get everything common denominator because it makes my math faster later. We're going to simplify it all down. I mean, because technically, right, 3 pi over 6, right, is pi over 2. So I know that simplifies down, but I'm going to have to simplify it all down, and I want to make sure I get all the solutions and I can do the integer k equals math as fast as I can. All right, so k equals 0, that first one, pi over 6, all right, and 3 pi over 6, which is pi over 2. K equals 1. So pi over 6 plus 4 pi over 6 is 5 pi over 6. See, do that math. And then 3 pi over 6 plus 4 pi over 6 is, oh, look, 7 pi over 6. So I can just do that math a lot faster.
All right, so then we have, I guess I'll write this one out. Pi over 6, I can do this one, we can do fast too, because it's 8. But this becomes 4 pi over 6 times 2, which then is 8, 9 pi over 6, which is actually 3 pi over 2. And 3 pi over 6 plus 4 pi over 6 times 2, which is 3 pi over 6 plus 8 pi over 6, which equals 11 pi over 6.
So, right, it's all just, we're just adding fractions, all right? Common denominator just helps us speed that up, all right? At 11 pi over 6, right, the next one, I can already see 3 times 4 is 12, 12 pi over 6, all right? 12 pi over 6 is 2 pi, which means 2 pi plus anything, I'm outside my range. So I know this is my last value.
All right, so hence theta equals 5 over 6.
Oh, and actually as a note, right, so we had this one, this is pi over 2, and 3 pi over 2 there. Those are actually both redundant values. So even though we solved them on that one, they were just repeated on this one. So you don't need to write it twice, right?
So pi over 6, pi over 2, 5 pi over 6, 7 pi over 6, 3 pi over 2, and 11 pi over 6. 6 solutions.
Also as a note, 3 theta, right? Which means the period is cut in 1/3, which means you should have 3 times as many solutions as the 2 we initially had. So you can count yourself again, other ways to logic check, right, as you're going through the problem as well. That's good stuff. I like solving these problems. Identities are pretty satisfying too for most of us. All right, one more question here. All right, solve sine squared theta equals 2 cosine theta plus 2 for our standard range. Actually, oops, slight difference. This one says including, so we'll have to be aware of that. For this guy, all right, and we talked about it before. I have sines and cosines. Now, our thetas are the same, which is always good news. But when you have both sines and cosines, you want to attempt to get them into just sines or just cosines. Good news for us. What wonderful identity do we have that does this for us? How can you convert just sines to just cosines or vice versa? But there are lots of ways, but there's the super easy one. Specifically, how about sine squared? Yeah, the fundamental. When you have sine squareds, and the only way, or the easiest way by far, is to convert the sine squareds to cosine squareds, right? Because I have cosine not squared in this equation.
So using the fundamental,
right? Or the adjustment of the fundamental identity. Sine squared theta equals 1 minus cosine squared theta.
which then becomes 1 minus cosine squared theta equals 2 cosine theta plus 2. Since I did the hard part, let x equal cosine theta.
And we just have an algebra problem.
When you have a quadratic,
Right? You always get it equal to what?
0, right? Get it equal to 0. So I'm gonna bring all that over. Let's see, we end up with x squared plus 2x plus 1 equals 0. Which is a perfect square. I could diamond this, but this happens to be a very clean solution.
And this is also very nice because cosine theta equals -1. All right. For what angle is the cosine function equal to -1? 5. All right. And again, only one solution. Angle wasn't adjusted. Easy peasy. All right. Algebra plus our trig. All right. Back and forth we go. All right. Best way to get better at something is what?
Keep doing it.
Keep doing it. All right. Practice, practice, practice. All right. We have no class on Thursday. There is all spring break. All right. We're going to start the lecture for chapter 7 on Tuesday upon our return, but basically you guys have 2.5 weeks, okay, before our quiz on this material. Take your time, grind, grind, grind. Best thing to do. All right, survive chapter 6, and trust me, it is mostly downhill. There's little rock patches, but mostly after chapter 6, all right, it is mostly downhill. All right, if you have any remaining questions, please let me know. Otherwise, have yourselves a wonderful spring break.